One of the most useful properties of the ring of integers that we use throughout all of mathematics is the fact that any number can be factored into a product of prime numbers, and this factorization is essentially unique. So we're going to start looking at factorization in abstract rings, and what we'll find is that many rings have factorization properties that are nice, that are very much like the integers, but many of them don't. And so we'll actually be able to distinguish a few different classes of rings based on partially on how their factorization works, how nice it is or how not nice it is. Now, in the integers, we factor things into prime numbers, and there are various properties that prime numbers have. And in the integers, these properties all happen to come together into prime numbers. However, in abstract rings, we can have elements that satisfy some of our standard prime number properties and not others. And so we need to develop some more precise language that we will use to describe elements in rings. So, section 1 in this factorization process is prime and irreducible elements. So we start with definition 121. First of all, we are only going to talk about factorization over domains. Factorization over non-domains tends not to have really any of the nice properties that we want. So let's let R be a domain. Two elements, A and B, are called associates if there exists a unit U such that A equals U times B. So recall that a unit in a ring is some element that we can divide by, that has a multiplicative inverse. And so there is some element U inverse that we could write down. And so to say that A is equal to U times B is the same as saying that B is equal to A inverse or U inverse times A. And what we're going to see is that associates are essentially considered the same when factoring elements, when looking at factorizations. Now, in the integers, two elements are associates if there exists a unit that that satisfies this relationship. The only units in the integers are 1 and -1. And so we certainly have that an element is associate to itself because A is equal to 1 times A. But we also have that the negative of a number is associate to it. So in the integers, 5 is associate to -5, for instance. A non-zero, non-unit element A in the ring R is called irreducible if whenever A equals B times C for some elements B, C, and R, one of B or C is a unit. So this says that an element is irreducible basically if it can't be factored into two things where neither one of them is a unit. Now, anything can always be expressed in terms of a product of units and other elements, but something's irreducible if it can't be broken up into two non-unit things. Furthermore, a non-zero, non-unit element A in R is called prime, or a prime element, if A dividing B times C implies that A divides B or A divides C. Now, you'll notice that our definition of irreducible looks like the definition that we're familiar with for prime numbers in the integers, and our definition of prime here is generally thought of as a consequence of that. It's a theorem that you prove about the prime numbers. And as it turns out, it's going to be more useful for us most of the time to talk about irreducible elements rather than prime elements when talking about factorization, although prime elements will show up occasionally. It turns out that in certain kinds of rings, including the integers, irreducible elements and prime elements are the same. But in some other rings, they are not. So, let's look at an example. Let's let R be the ring Z adjoin the square root of -7. Now, this is a ring whose elements look like A plus B times the square root of -7, where A and B are both integers. And addition and multiplication are handled in the standard way with the note that if you take the square root of -7 times the square root of -7, then you get -7. So this is an interesting ring. We can see it as a sub-ring of the complex numbers, where we include all the integers and some element of the complex numbers whose square is -7, and then form the ring of all possible combinations of those. Now, in order to understand this ring, and we're going to come back to this example multiple times throughout this chapter, we're going to define a function, n, sometimes called the norm of this ring. Let n from R to the integers be given by the norm of an element A plus B times the square root of -7 is equal to A squared plus 7B squared. Now, there are a few things that we're going to be able to note from it. The most important property that we're going to look at is the fact that n of a product is equal to the product of elements. So the norm of a product is equal to the product of the norms. This is for all x and y belonging to R. This requires a little bit of check, but it's simply a fairly straightforward calculation where you evaluate both of these, and you notice that the product works out the way that you want it to. Also, we can see that the norm of an element is equal to 1 if and only if x is a unit in R. In fact, the only units of this ring are 1 and -1. The same as the units of Z itself. Okay, so we're going to look at a particular element of this ring and show that it is irreducible, but it is not prime under the definitions that we just gave, showing that in this ring, the two notions there fail to coincide. So let's consider the element A, which is 1 plus the square root of -7. We claim that A is irreducible, but not prime. So let's suppose that A is equal to B times C, where B and C are non-units. We have then that the norm of b times the norm of c would be equal to the norm of bc. That's this property up here that we noted can be proved for this function, which is the norm of a, and the norm of a is equal to 8. So we must have that one of n of b and n of c must be 2, and one of them must be 4. We have assumed that b and c are non-units, and therefore neither of them can have a norm of 1. So we've got two numbers, neither of which is 1, that multiply to equal 8. Then it has to be the case that they are 2 and 4. So 1 of n of b and n of c is 2. But this is a contradiction. Since if I take any integers m and n and compute the norm of the element m plus n to times the square root of -7, we get m squared plus 7n squared, which is not equal to 2. And this is for any m and n in Z. So what this shows is that our supposition up here that A is equal to B times C, where B and C are non-units, leads to a contradiction. And so we have that A is irreducible. We cannot express A as a product of two other things where neither of them are units. However, we're going to show that A is not a prime element. So what we're going to do is we're going to demonstrate that there's some element where A divides, let's see, I don't want to duplicate any of the numbers that, or symbols that we're going to use. We're going to find an x and the y such that A divides xy, but A does not divide x and A does not divide y. This will show that A is not prime, because a prime element would say that if you divide a product, then you have to divide one of the factors in that product. So let's notice that A times 1 minus the square root of -7 gives us 1 plus the square root of -7 times 1 minus the square root of -7, which gives us 1 minus the square root of -7 plus the square root of -7 minus the square root of -7 squared, which is -7, which gives us 8. And also that 2 times 4 is equal to 8, of course, because the integers are a subring of our ring, so 2 and 4 exist in there. And so what we have is that basically 8 can be factored in a couple of different ways. This is also an illustration of the fact that this ring has the property that that things do not have unique factorizations. So we have that A divides the product 2 times 4. Now, if A were to divide 4, then there exists a B somewhere in the ring R such that A times B equals 4, and hence we would have that 16, which is the norm of 4, would have to equal the norm of A, the norm of AB, which is the norm of A times the norm of B, and we worked out earlier that the norm of A is 8. So we'd have 8 times the norm of B. So that means that the norm of B would have to be equal to 2, which we've already seen is a contradiction. So that means that A does not divide 4, and if A does not divide 4, then A certainly does not divide 2, because if it divided 2, it would divide 4. So that means that A is not a prime element. So the rings Z adjoin the square root of a square-free integer, and especially the negative of a square-free integer, are often very good rings for understanding how factorization and irreducibility and being a prime element can behave in ways very differently from the integers. As we see here, we have that we have the element a, 1 plus the square root of negative 7, which is irreducible. It can't be broken up, but it's not prime because it divides a product without dividing either of the two factors involved. So we've got something that's irreducible but not prime. The question is, can we find something that's prime but not irreducible? And the answer to that is no. No, we can't. Theorem 122 tells us that let R be a domain and A some element of R. If A is prime, if A is a prime element, then A is irreducible. Proof of this is fairly quick. Let's suppose that A is prime. We want to show that it's irreducible. So what we can do is we can say, let's let B and C be elements of R such that A is equal to BC. And we want to show that one of B or C must be a unit. Now, since A equals BC, we certainly have that A divides BC, and since A is prime, we have that A divides B or A divides C. Without loss of generality, let's suppose that A divides B, so that means that B is equal to A times D for some element D in the ring. Therefore, we have that A is equal to BC, but B is equal to AD. So that's ADC. Now, R is a domain, so we have cancellation. So by cancellation, we have that A is equal to ADC. If we cancel the A's on both sides, we get that 1, the multiplicative identity, is equal to DC. Thus, C is a unit. So that means that A is irreducible. So all prime elements are irreducible, but in general, some irreducible elements may not be prime. Now, that said, the two notions do coincide, as we see in some cases. For example, they coincide in the integers. And in general, they coincide for principal ideal domains. So theorem 123, let R be a principal ideal domain. Remember, that means that every ideal is generated by a single element. For A, an element of R, we have that A is a prime element if and only if A is irreducible. Half the proof is, of course, already done. By theorem 122, if A is prime, it is irreducible. So now, let's suppose that A is irreducible, and we want to show that it is a prime, that it is prime. All right, so let's let B and C belong to the ring R such that A divides BC. That means that there exists some D in the ring such that A times D is equal to B times C. So now what we're going to do is we're going to have to take advantage of the fact that R is a principal ideal domain, which means we need to look for some sort of ideal. In this case, as it turns out, what we want to do is let I be the ideal generated by A and B. So this is the set of all combinations of A and B that you can get by multiplying each by some element of the ring and adding them together. That's an ideal of the ring. But since R is a principal ideal domain, there exists some element P in the ring such that I is equal to the ideal generated by P. Every ideal is principal, which means every ideal can be generated by a single element. Now, since A and B belong to the ideal, they're generators of the ideal, that means that there exist Q and R in the ring such that A is equal to PQ and B is equal to PR. And we know that since A is irreducible, that was what our hypothesis was, and we have that A is written as P times Q, we have that P or Q is a unit. One of those two is a unit. Now, let's consider those two as cases. So if P is a unit, then that means that I is an ideal containing a unit, which means that I, in fact, has to be the whole ring R by an exercise. So in particular, this means that the multiplicative identity belongs to the ideal I. So we can write that 1 is equal to, the ideal I, remember, is still generated by A and B, which means that every element of the ring, every element of the ideal, such as 1, can be written as a combination of the A and the B. So in particular, this means that 1 is equal to AV plus BW for some V and W. So we're trying to prove that A is prime, which means we're trying to show that A divides one of B and C here. We have this, and now we're going to multiply both sides by P. Sorry, not by P, by C. Multiplying both sides by C, we get that C is equal to ACV plus BCW, but BC was A. So this is ACV plus AW, which is A times CV plus W. So this means that A divides C. A times something is equal to C. So that's all great. That happens if P is a unit. So let's see what happens if Q is a unit. Now, if Q is a unit, then that means that then the fact that we have that A is equal to PQ, that means that P is equal to Q inverse times A, because Q is a unit, we can do that. So, in particular, this means that B, which is equal to P times R, is equal to Q inverse times A times R. And so that means that A divides B. So we have that in any case, either A divides B or A divides C, and so that means that A is prime. So this means that in principal ideal domains, such as the integers, in polynomial rings over a field. All right, so this is when F is a field. We know that both of these are principal ideal domains, and in any other PIDs that we run into, we have that prime elements and irreducible elements are the same. If we aren't in those situations, we have to be more careful and make sure that we're making appropriate distinctions between prime elements and irreducible elements when we encounter them.